Thanks for watching. If you enjoyed this video, please hit the subscribe button and ring the notification bell so you never miss an update. Leave a comment below to help grow the channel, and don't forget to smash the like button. Lecture 95, this is the first lecture in the new semester. This is on calculus Lite-Tangent lines. So the reason I'm doing this is because last semester when we talked about the wave equation, we found it rather difficult to write the wave equation in a notation that wasn't nonsensical. So I'm going to try to remedy that by introducing some of the notation that we use in calculus, and that's our main goal, is to just understand the notation and what it means, okay? And so for that, I'm going to kind of run you through in 2 lectures a brief overview of calculus and the kind of problems that we solve and the notation we use to represent that stuff, okay? Does that make sense?
Yes.
So there were 2 big problems, you know, in like the 1500s and 1600s, the time when Newton was young, that people were worried about. And those problems were tangent lines, finding a tangent line to a curve, and finding areas underneath curves. And they suspected there was a relationship between these 2 things. And this turns out to be what we call the fundamental theorem of calculus, which we're not going to state today, or maybe we'll state it tomorrow, or in the next lecture. But today we're going to talk about tangent lines, okay? So what is a tangent line? It's a line which just touches a curve in one point without changing sides on the curve, okay? So the easiest tangent line to get, right, is a tangent line to a circle. So if I draw a circle whose center is some point C, and I'm just going to pick a point, we'll call it the point P on the circle, right? We can easily construct a radial line. I guess I could use my fancy whiteboard ruler. And I'm also going to put some orthogonal axes on here as well. There we go. And why did I do that? Well, so this line, R, right, is always perpendicular to the tangent line that we might construct, pass it through this point. I guess I could use this again to make my tangent line. Now, technically it's supposed to be touching, but it's not quite. Okay, so this is the point P. By definition, this radial line is always normal to any point on the circumference, right?
Yeah.
That is kind of the definition of these things. And so we can easily construct a tangent line, which is just perpendicular to that radial line, by constructing a perpendicular to it, right? We know how to find if we know the equation of the line for this, right, then we can find the equation of the line for this tangent line. So let's say, what is the equation of the line for this? Well, actually, that's why I want to put the axes on here, because I want to measure it out like this. If this radius makes an angle theta, what we'll call the, I guess, the x-axis, right? This will be the y-axis, right? Then this point, P, right, is going to be given by, well, its x component, right? That's just r times the cosine of x. That's r cosine of x. And the y coordinate here is just r sine of x. Everyone remember that?
Yeah.
Yeah? So now we can easily construct the equation for the line, for this radial line. Okay, how do we do that? Well, it's y minus, remember the point slope form of a line, right? Y minus y naught. So y naught will be at the center, which we'll assume is 0, 0, okay?
All right.
So y minus 0 equals the slope of the line, which I'll just write as m for now, times x minus x naught, which again is 0, so it's just x. So what is the slope of this line? Well, that's the rise over the run, right? So the slope is just going to be given by the rise. The rise is r sine x, right? R sine x. I keep saying x, and it's supposed to be theta. You guys got to catch me when I do that, huh? Theta. By this angle theta. Divided by r cosine theta. That's the run, right? So it's this component, r sine theta, divided by this component, r cosine theta, right? The r's cancel, because it's in both the numerator and the denominator. And so our slope is given by the tangent of theta, or sine theta over cosine theta. And the equation of the line is just y equals tangent of theta times x. So that is this radial line, okay? Now, of course, it goes out forever in all directions. Now, what if I want to construct a perpendicular to that line? How do I do that, right? A perpendicular line, right? That is what we want for our tangent line. The only other thing I would say is that we want it to be centered at P, so we'll have to deal with that complication in a minute. But in general, how do you get a perpendicular line if you know this line is given by y equals tangent of theta times x? Well, the rule for finding a perpendicular, I'm going to call this y sub r for radial, okay? You could also call it like y sub n for normal, right? It's the normal line to this circle. The tangent, though, which I'll call y sub t, is equal to minus 1 over m times x for this, okay? And so that would be minus cosine of theta divided by sine of theta times x. But that, of course, is a line that's still centered at 0, 0. We would really like it to be centered at the point P, right? So how can I adjust that to be centered at point P? Well, I'm going to have to do y sub t minus this y value, right, the new center, r sine theta, equals the slope, which is the slope for this tangent, right, minus cosine theta over sine theta, it's just the reciprocal of this, right, times x, all times x minus, now we need this point for the center, r cosine theta, okay?
Okay.
So there is the equation. Now you can, of course, solve it for y sub t. You can distribute all this stuff if you want to, and that will give you a line, which is this line right here. Its slope is negative, right? Here we had a positive slope, so now we have a negative slope for this tangent. You see that?
Yeah.
Does that make sense?
Yeah.
So for a circle, it's relatively simple, right, to find a tangent line for a circle. Okay?
All right.
So why is that useful? Well, because if I have any curve, right, don't need this anymore. If I have some arbitrary curve in space, let's just say something like this, okay? And maybe I want to know what the tangent line at this point is, right? If I can simply find the circle which touches this curve only at that point, right? And I can figure out, and here's again, we'll call the point P, and I can figure out what the center of that circle is, right? You can have virtually any radius that you want. That's not important. Finding the center of that circle that just touches this curve at that point, right? If you can do that, well, now you can then construct a radial line, and then from that you can construct its perpendicular to that, and really all you need is the slope, because all you want to know is what's the slope of the line at this point that is tangential to this, right? So I'm looking for the slope of that tangent line, okay?
All right.
And this is how they would have done it, right, before Newton and the calculus that he invented, okay? And I think it was Viet, I'm not sure who it was, that devised a procedure for finding the centers of these circles that will touch these curves in just this way so that you can then find a tangent line to the point on that curve, okay?
Okay.
So keep that idea about these tangent lines and their slope. It's really just the slope of that tangent line that you need, okay? Keep that in mind, and let's recall the idea of average velocity, okay? With this, we'll say is t. With this, we'll call x. And let's do something simple. Let's do this curve right here, right? So if it times 0, I am located at point 0, or I haven't gone anywhere yet, right? We'll just call where I started times 0 our starting point. And then later at some time, t, we are at this new point, x, right? The velocity, or the average velocity, is just, I'm going to write v, a, v, g. Average velocity is just this delta x divided by delta t. where you'll remember that this is like, we call this x final minus x initial divided by t final minus t initial. Does everyone remember that?
Yes.
But what if I got here by a different route? What if I had taken a slightly different way to get there? So maybe my real curve looks something like this, okay? And maybe I'm no longer interested in the average velocity at this point, but let's pick this point right here, okay? Well, for the straight line that I drew before, right, that's, you might recognize as a constant velocity, which means that the slope of this line is never changing, right? This is a line that has one slope, right? It's
Yeah.
delta x over delta t. So now I'll change my point of interest from this point here down to this point here. So this is what I'm interested in, okay?
All right.
So we're getting to the same place in the same time, right? So the average velocity for both of these curves, the curve path up here and the straight line path down here, right? The average velocity is the same, okay?
Yeah.
But the instantaneous velocity along the way is not, right? So if I wanted to know, well, what is the velocity at, say, this point here, right? Well, what I really want is a tangent line to this, yes?
Yeah.
You can see that that tangent line is a bit less steep than, say, this tangent line is here. But if you look at it earlier on, right, and say this point here, this tangent line was steeper, right? So let's, does everyone kind of get that idea?
Yes.
Yeah. But how would we figure out what this is, though, right? So let's get rid of the straight line. Let's not worry about that old average velocity anymore. And let's just think about how would we get the tangent line at this point. This is the point we're interested in here, okay? Well, we could take a point, say, here, and say another point here, and we could construct a line that connects those 2 points, yes?
Yes.
That would give us an approximation to what the velocity is at this point here, right? Because that's the average velocity between here and here. But it should be obvious that I can make it more accurate by bringing these 2 points closer to the point of interest. So if I say, well, you know what, I think I want to make this point here and this point here, use that to find this tangent line or this instantaneous velocity. And you can see that it's getting closer to what it would look like for an actual tangent line, okay?
All right.
And we can squeeze that in tighter and tighter as much as we want. And let me give you an example of this squeezing and what it looks like. I forgot that doesn't like to stay up that way. I want to take the number 1 and I want to subtract a little bit from it, okay? So I'm going to try to make a little table. I guess we'll call this like in values. Call this delta t sub ins. And then we'll call this our t sub ns, numbers, okay? So for n equals 1, I'm going to say my delta t1 is equal to 0.1. And t sub n is going to be equal to 1 minus this delta t1, right? Which is just 1 minus 0.1, so that makes that 0.9, okay?
All right.
For n equals 2, we'll let my delta t2 be equal to 0.01. So that now 1 minus delta t2 is equal to 0.09. Nope, 0.99, sorry. Okay?
Yeah.
And you kind of see where I'm going with this, right? 3 would be delta t3 equals 0.001. And t sub n is 1 minus delta t3, which is equal to 0.999. Okay? And I can keep doing this on and on and on, right? All the way to n equals infinity, right? Where I don't really have a way to write a delta t infinity, I guess. It's just a whole bunch of zeros, and then finally, I guess, a 1. You can't even really write it, right? So let's just say that. That's going to be 1 minus this delta t n, which is going to be equal to 0.9 repeating forever. That's how we write it, right? That means it just 9's all the way back, right?
Yeah.
So this is, say, a secant. We call these secant lines, okay, from before. And the point that just touches the curve, we call that a tangent line. So I want you to think of these approximations as secant lines that are getting better and better and better. They're getting closer to what we really want, which is a tangent line, okay? Remember, the secant lines pass through the curve at 2 points. The tangent line only passes through at 1 point. Similarly, in what I've written up here, where I'm subtracting a little tiny bit, and then a little bit more, right, 10 times more, I guess you'd say, in the next interval, making it closer and closer to the true value of 1, right?
Yeah.
Notice that any of these, right, if I take t sub n, right, this is, we'll call this t sub 2, right, which was equal to 0.99, right? I can make that equal to 1 if I simply add back this delta t2, 0.01, right? If I add 0.01 to this, right, then I get my t value back. Yes?
Yes.
Well, what do I have to add back? What can I add to 0.9 repeating to get me 1?
What repeating?
Nope. That would be 1.1 repeating. 0.9 repeating is it's equal to 1. These are equal, okay? This is equal to 1. It is the same thing, okay? So when we take this limit of taking a smaller and smaller bit off of 1, right, ad infinitum, right, then our final answer, right, our tangent line, if you will, is the same thing as this, okay? It's a hard idea to wrap your mind around. And if you don't fully understand it, don't worry about it. Just think, you know, of a tangent line as the final form of the secant line, right? But that's the difference, right? The secant line passes through 2 points on the curve, but doesn't change sides, right? Except for that brief interval between the 2 points, right?
Yeah.
The tangent line only goes through 1 point, okay? It's very much like 0.9 repeating is exactly the same thing as the number 1. There's no difference in those. There's nothing you can add to 0.9 repeating that will give you 1. It'll always be greater than 1. So if I add any teeny tiny little bit, no matter what, it's always greater than 1. It must be. And if I subtract any little tiny itsy bitty bit, it's less than 1. There's only one possibility left. If by adding a little bit, it's greater than 1, and by subtracting a little bit, it's less than 1, that must mean it's equal to 1. So 0.9 repeating and 1 are the same number. Okay?
All right.
Tangent lines are a little bit like that, right? It's this kind of this ultimate limit. Okay? When you make the points closer and closer together, the 2 points in a secant line, when they get infinitely close together, right? It's kind of the same thing as 1 point. Okay? But again, if you don't fully appreciate that, then don't worry about it. But that's the idea behind these limits. So this is something Newton really understood, Leibniz really did not. I forget what Newton's statement was about ultimate ratios, but it was a big put down for Leibniz's form of calculus. But we'll actually look at Leibniz's form of calculus because it's an easy way to get an idea of how we do this stuff. This is the notational part. So you remember that we had like average velocities were like delta x over delta t, right?
Yeah.
So in calculus, what we're going to do is we're going to replace these deltas, right, which always mean changes, right? So delta x would be x final minus x initial, right? Yeah. These are going to become little d's, okay? Remember, delta is the d. This is the uppercase d for Greek, okay?
All right.
So they're going to become little d's, lowercase d's, dx over dt, okay? That's the thing that we're interested in now, okay?
Yeah.
So we replace these deltas with these d's. This is that, let's go on down to infinitely close, right? We're bringing those 2 points infinitely close together so that the 2 points are now just 1 point, just like 0.9 repeating is really just 1, okay?
Yeah.
And so that's what that means, okay?
Yeah.
It's really very similar to this, okay? And if you want to, you can think of it as like this, just really small deltas, really tiny deltas, and that's fine. It's not going to hurt. But we're going to take it one step further. This is where it's going to be really helpful in writing down certain types of equations that are fundamental and important in physics, like a wave equation, for example, because I now want to think of this dx dt as some operator operating on x. It's like a function. Remember what a function is, right? F of x. It takes something from one set and maps it onto another set. Okay, and the function f, the reason we call it that is because that's the thing, that's the operator, that's the mapping, that's the thing that takes values from here and finds their corresponding place in the other set. Okay, And so we can think of this thing as an operator. We call that operator the derivative. Okay? Why it's called a derivative, I think maybe because if you think of like velocity as something that comes from position versus time data. If I know the position of an object at various points in time, right, then I can find its velocity. So we derive its velocity from its position information, you see?
Yeah.
So I think that's probably why it's called that, but I don't really know. But we want to now think of this as an operator. We're going to call it the d over dt operator. We just call it the derivative, or the time derivative, if you will. Okay? And it operates on x. So I actually separate this out. And it doesn't make sense with the delta notation to do that, right? That's the trouble we ran into with writing the wave equation. Okay? Because we had to do this operation twice. Okay? So here's one operation. It's called the derivative operation. And if I let it operate on just x, right, then it's just our old friend dx dt, where you can think of the dx as a delta x, where the delta is really small, divided by a dt, which is just like a delta t, but with the delta very small, okay?
All right.
But we're kind of abstracting in a way, and we're thinking now more generally, and we're thinking of this as an operator called the derivative operator. You can think of it as find the slope of the tangent line at that point operator, okay?
All right.
So if I said, you know, d over dt of f of t, f of t naught, I'll say. That says find the slope of the function f at the point t naught, okay?
Okay.
That's how we want to think about it. And we can do this operation more than once, right? Once you found that slope, right, you're going to get a functional form, right? So if I say what's the derivative of a function, I'm asking for what's its slope at every point. And if I have that, then I have another curve, right?
Yeah.
And now I can say, well, let's find derivative, let's find the slope of all the points on that curve that we got, right? So we can do two operations, right? So I can say, okay, let's do d over dt of d over dt of some function which is called y, okay?
Yeah.
So I first take the derivative with respect to time of y. I find the slope at all points on y, right? And then that gives me a new curve. You could call it something else. You could call it, I'll call it z, right? So if d over dt is equal of y is equal to z, right, then this is just d over dt of z, right? You see that?
Yeah.
So we already know how to do that. We have a curve, find the slope, right, of the tangent line at every point on that curve. But what we can do is we can write this differently. We can say like this, d2y over dt squared. That's applying this derivative operator twice, and that's how we would write it notationally. And that's what we want to be, well, that's the way we want to represent things for in a wave equation where we have second order derivatives in space and time that we have to take, okay?
All right.
It just tells us we apply this derivative operator twice, okay?
Yeah.
And there's just no neat way to write it with deltas. It just comes out looking silly and not making a lot of sense. Here it makes more sense. It just means we're applying this operator first to this function, and we'll get a new curve. And now we do the same thing. We find the tangent line at every point on this new curve, right? So that's two derivative operators, you see?
Yeah.
And that's how we write it, d2y over dt squared, okay? Because the dt squared part, it really is kind of like dt times dt. It's like a squaring it. But doing an operation twice, right, is not the same thing as squaring y, okay? Anyways, so that's the notation, okay? A little bit more notation. And this, I think it comes from Newton. If we want to write a time derivative, because physics is usually talking about either derivatives with respect to space, right, x, or derivatives with respect to time, t. And so if we have a time derivative, so let me just write this. D over dt, or df over dt is the same thing. We can write this equivalently as f dot. Okay? If we took two derivatives, right, if we had d2f dt squared, we would write that as f double dot. You could do 3 and have f triple dot, okay, but it just saves space to write it as f dot, okay?
All right.
If this, however, was a spatial derivative, so if we had, say, d f dx, then the preferred way to write that is f prime, and d2f dx squared, the second derivative with respect to x, we would write as f prime prime, okay?
All right.
So if you write the primes, that means you're taking a spatial derivative. If you write the dots, it means you're taking a time derivative. And it's just a way to save space and writing stuff down, because you don't have to write this over and over again, right? It gets ugly. And I know Newton used this format. I don't remember if he used this or not, but this is very common today for spatial derivatives. Let me just give you a feel for how this calculus stuff works, okay? So this is a variation. This is Leibniz approach, and it's not in any great detail. It's not exactly right, but it's the general idea, okay? So let's say I want to find the derivative for the curve y equals x cubed, okay?
Yeah.
I'm doing y equals x cubed because I saved y equals x squared for you guys to do in a homework assignment. It's easier. So I give you the easy one, I'll do the hard one, okay?
All right.
So what you want to think of is, well, I want to change this a little bit. I'm going to vary this a little bit. So I'm going to add a little delta x, but I'm going to make it really small, so I'm going to call it a dx, okay?
All right.
So I'm going to change x by a little bit, x plus dx, you see? If I change the x value, the y value is going to change a little bit though, right? So this will become y plus dy, okay? So far, so good. Now we just need to do algebra, okay?
Yeah.
I got to cube this. You guys remember the binomial theorem, right? How can we do, if this was to the fifth power, right? Instead of multiplying this thing a whole bunch of times and canceling and recombining, there's an easy way to do these problems, right? This is just going to be, it's going to be something times x cubed plus something times x squared times dx plus something times x times dx squared plus something times x to the 0, which we just won't write, times dx cubed, right? And what goes in front of these values, right? Well, this is going to be 3 choose 0. That's the coefficient that goes here. This is 3 choose 1. What goes here is 3 choose 2. And what goes here is 3 choose 3, right? 3 choose 0, right? That's just 3 factorial divided by 0 factorial times 3 minus 0 factorial, which is just 1. So that gives me 1. This gives me 3. This will also be 3, and this will be 1, okay?
All right.
If you don't remember how to calculate the n choose k stuff, then let me know and I can walk you through it again. It's not hard. Anyway, that's how you can multiply these long. So if I were to multiply this out manually, this is what I would end up eventually after I simplify everything, okay? And so that's still equal to y plus dy, right? But notice we have x cubed here, right? X cubed is just equal to y, right? So I can replace this x cubed with just a y again. You see that? Yes?
Yes.
But we have a y on the left, a y on the right. Why not just get rid of them? We can subtract y from both sides, and it gets rid of them, right? So I got rid of y. I'm left with just dy on the right, and some stuff that's got dx's on the right. I'm sorry. We have dy on the left, and stuff with dx's on the right. Yes?
Yes.
Well, let's divide by dx, because remember, we want, what are we doing here? We want this dy dx thing, this derivative thing, this that I have related to earlier, means the tangent line at a particular point, right?
Yeah.
If we have the formula for it, that gives us the tangent lines for all points on this curve, okay?
All right.
And that's what we're aiming for here. Instead of getting a particular tangent line at one particular point, we're doing some algebra and we're finding the tangent line at all points on this curve, okay?
Okay.
So this is what I want. I want dy dx. I've got dy, right? Let me just divide everything by dx, okay? So if I divide dy by dx, which is what I want, that says this is equal to 3x squared. This dx just got divided out, right? Plus 3x times dx squared divided by dx is just dx, plus dx cubed divided by dx is dx squared. Yes?
Yeah.
All right, well, that's some kind of answer, but I still got a bunch of dx's in there. I'm not sure what do I do with that, right? Well, at this point, what we want to do is we want to take the limit, right? We'll say that dy dx in the sense of, our derivative definition, right? Here we're just thinking of a ratio of some really small numbers, right? Here I'm thinking of this derivative idea, right? This is going to be equal to the limit. Not surprised like this. The limit as dx approaches 0, right? We're going to make very small differences, right? Of 3x squared plus 3x dx plus dx squared. And what does this limit look like? As dx approaches 0, this will go away because this dx becomes 0. This will go away because if I square it, it approaches 0 even faster. And I'm left with just this one term that's equal to 3x squared. So this is telling me that the derivative of the function y equals x cubed is the function y equals 3x squared. Okay?
All right.
That's what we found using this algebraic trick. Well, it's not a trick. It's doing some algebra and using this idea that really comes from Leibniz on taking the derivatives. Okay?
All right.
Newton had a funny way of doing it, and I don't actually, it's hard to teach it that way, but for people that know calculus, he basically parameterizes independent variable. So if you have a y versus x graph, you would parameterize y and x in terms of t. He was thinking of time. He's thinking that these points on these axes have some time dependence, and they're moving in time. He called them mechanical curves, okay, because they're moving. And it's if you already know calculus and seeing how it's done, you're like, oh, that's kind of cool. It's just he's parameterizing the equation in terms of the parameter t. But if you're learning calculus for the first time, it would totally confuse you, okay? Whereas the way Leibniz did it with these simple ratios, right? So he treats these differentials, differential divided by differential. He treats these differentials, right, as real ratios. That's not actually correct, but you know, you can think of it that way when you're getting started in this stuff. But anyway, so that's what you can do. You can do this for anything. You'll do it in the homework assignment for y equals x squared, right?
Yeah.
You'll see that it's not that hard. Just a little bit of algebra, and you're just trying to rearrange everything so that you get one of these guys, and then you take the limit, right, as these dx's go to 0, and you see what's left over, right? And we get this is equal to 3x squared. So, turns out that there are some basic rules for taking derivatives that you'll eventually learn in your calculus class when you take it, but I'll give you the basic ones here because you don't need to know any. If you understand what the notation is trying to do, then knowing what the quick rule to get the answer is I think, useful. So let's write d over dx of x to the n. So if I have, that's a polynomial, any polynomial. It's x cubed, x squared, x to the 9th, right? The derivative with respect to x of that is equal to n times x to the n minus 1. Okay, so if it was x cubed, it's going to become 3 times x to the 3 minus 1, or 3x squared. What we found in the last example, right?
Yeah.
If it's x to the 4th power, right, it's going to be 4 times x cubed. Okay, that's the rule. You want to take a derivative of a polynomial, that's what you do. Okay,
All right.
you got that?
Yeah.
Here's some other ones that are handy. What about d over dx of the sine of x? That is equal to the cosine of x. D over dx of the cosine of x is equal to, what do you think it's equal to? Take a guess. So we found that I stated that d over dx of the sine of x is equal to cosine of x. What do you think the derivative of cosine of x is equal to?
Sine of x.
Almost. It's minus the sine of x. Minus the sine of x. There's a sign change that takes place. Okay.
All right.
You have to go around twice to get it back to a positive value. But anyway, one more. D over dx of e to the x power, that's the exponentials, is equal to e to the x. Well, isn't that cute? That is really, that's what an exponential is, right? It's a function whose derivative is itself.
All right.
That's what makes it special. That's why the number e is this special number. I think that's it. These will be useful. Anything else I want to say? No. Hit the basic derivatives that you can use on the fly. And so this is, coming to understand this stuff and how to use it. Plus, there's a couple of things you need to learn: the chain rule and the product rule. That is basically what you learn in a first semester calculus course. Okay.
All right.
But the idea behind it is pretty simple. It's just the slope. It's the slope of a tangent line at any particular point on a curve. Okay. Yeah. So, and that has particular importance towards calculating rates of change, which is important in science, right? Whether it's physics or chemistry, rates of change. A lot of what we do, right?
Yeah.
That's it. Any questions?
No.
No. Okay.